The world's richest man just made a shocking announcement about space that has left everyone speechless. Elon Musk claims that we can finally see inside a black hole. This is something that everyone knows is impossible, so you can imagine the awe it brought on people. But the most jarring thing about this announcement wasn't just that it was impossible, but that people couldn't wrap their heads around how this act could be done. So it begs the question, what equipment could possibly see into a black hole? Is it really possible? Join us as we explore all the answers to your questions. Discovery of first black hole. We all know Elon Musk is the man who dreams of turning science fiction into science reality. And it's true that he isn't known for studying black holes directly. But in his own way, his ambitions and innovations reach for the very edges of black hole science. This is mainly because of his interest with space and humanity's future in the stars. That is an interest that many have called an obsession or infatuation. But perhaps it is this supposed obsession that made people take his words seriously when he announced that we can finally see inside a black hole. A very shocking announcement because the very existence of a black hole doesn't support the idea of being able to see inside it. Does it sound a little tricky? Well, tag along as we iron out all the details for you. Imagine looking up at the night sky and wondering what lies out there in the endless sea of stars. Well, it's better for us because we actually have a snippet of an idea of what could be out there. People in ancient times did not. For centuries, humans looked up and wondered cluelessly. The idea of a black hole, something so strange and powerful that not even light could escape it, wasn't something ancient astronomers considered. But as science and imagination evolved, the concept started to take shape in the minds of brilliant thinkers. To better understand what a black hole is, let's dive into the journey of how the very first black hole was discovered, told in a way that feels like you're traveling along with the people who made it happen. It all started with a bit of mathematics and wild thinking. Long before anyone even thought about spotting a black hole, some physicists in the 18th century, like John Michelin, Pierre-Simon Laplace, wondered if there could be objects so heavy and dense that their gravity wouldn't let light escape. They didn't call these things black holes because that term wouldn't exist for another 200 years. But the seed was planted and the idea stayed quietly in the background until Albert Einstein came along in the early 1900s. Einstein's general theory of relativity completely changed how we understand gravity, space, and time. But Einstein himself wasn't convinced such things could actually exist in nature. A few decades later, other brilliant minds began pushing this idea further. Scientists like Carl Schwarzschildon Subramanian Chandrasekhar played with Einstein's equations and found that these theoretical objects weren't just possible, but could actually exist. Still, it was just numbers on paper. No one had ever seen or even thought they could see a black hole. After all, how do you look at something that doesn't let light escape? So you see where the problem with Elon seeing inside a black hole is? Let's look at the 1960s, a time when humanity started looking at the universe in new ways. Radio telescopes, which capture signals beyond what our eyes can see, became more advanced. Astronomers noticed strange objects in the sky, including a particularly curious star system called Cygnus X1. This system wasn't just a star, it was emitting massive amounts of X-rays, something stars don't usually do. These X-rays seemed to come from something pulling matter off a nearby star. It was a hungry, invisible companion. This was where the excitement began. Scientists like Tom Bolton and Louise Webster started to suspect that the mysterious X-ray source wasn't just any object. They studied the motions of the visible star in Cygnus X1 and realized it was orbiting something incredibly massive, yet completely unseen, a black hole. The invisible companion was so heavy and so compact that it could only be what the equations had predicted all along. In 1971, Cygnus X1 became the first object officially identified as a black hole candidate. It was a moment that felt like science fiction turning into reality. People were fascinated, and the discovery sparked new waves of curiosity about the universe. What else was out there, hiding in plain sight? Could there be more black holes scattered across the galaxy? Scientists now had a real target to study, proving that these once theoretical monsters were not only real, but also detectable if you knew how to look. And they didn't stop at one, they continued looking, and you won't believe the groundbreaking discoveries that have been made so far. Other knowledge about black holes. But it's not just the efforts of the scientists, although that cannot go without being mentioned. It is as though since the first discovery of a black hole, the universe hasn't stopped surprising us with more incredible revelations. It's as if uncovering Cygnus X1 threw open a door that no one even realized was there. And on the other side was a realm of mysteries more fascinating than anyone could have imagined. Scientists quickly realized that the black hole story was just beginning. And as they started to dig deeper, what they found changed everything we thought we knew about space. Black holes, it turns out, come in different sizes, like cosmic creatures ranging from small but fierce to unimaginably massive. After Cygnus X1, researchers began to notice that black holes could be far more varied than expected. Some of them were just a few times the mass of our sun, while others were millions or even billions of times heavier. The small ones, called stellar mass black holes, form when giant stars reach the end of their lives and collapse under their own weight. But the enormous ones, the supermassive black holes, seem to sit right in the centers of galaxies, including our own Milky Way. This idea of supermassive black holes at the heart of galaxies led to some jaw-dropping discoveries. It wasn't just that these gigantic black holes existed. They seemed to play a central role in shaping galaxies themselves. Imagine something so strange and powerful that it not only devours stars and gas, but also helps decide how an entire galaxy forms and grows. Observations of stars orbiting wildly around a mysterious, invisible center in the Milky Way confirmed the presence of a supermassive black hole, later named Sagittarius A. Gare. The motions of those stars were like tiny dancers spinning madly around an unseen partner, proving that this black hole was there, quietly holding everything together. But the universe had even more surprises in store. For a long time, scientists thought black holes were completely invisible unless they were actively feeding on matter, like in the case of Cygnus X1. Then in 2015, something unbelievable happened. An entirely new way of hearing the cosmos was revealed. Two detectors called LIGO picked up tiny ripples in space-time itself. These ripples had been caused by two black holes smashing into each other far away in space. Their collision was so powerful that it sent waves through the very fabric of the universe. It was the first time humans had detected something so otherworldly, and it was also the first direct evidence of black holes merging. This discovery was like adding a new sense to our understanding of space. Not only could scientists see the effects of black holes with telescopes, but now they could also hear their cosmic symphonies through gravitational waves. This opened a whole new way of studying the universe, revealing not just black holes but also the dramatic stories of their collisions, dances, and deaths. The first detected merger turned out to be just the start, and soon scientists were finding more of these cosmic crashes, each one telling a new story about the life of black holes. Then, in 2019, something extraordinary happened. For the first time ever, humans captured an actual image of a black hole's shadow, which we will delve deeper into soon enough, so keep watching. Each discovery has revealed something new, showing that black holes are far more dynamic and influential than anyone ever guessed. They aren't just cosmic vacuums sitting passively in space. Instead, they're engines of incredible power, shaping galaxies, bending light, and warping time itself. They've also turned out to be more common than expected, scattered across the universe like hidden gems, quietly lurking in places we're only just starting to explore. First picture of a black hole. As humans, we have made sure to explore and seek black holes at wherever they are, and what we found was just out of this world, literally. For the longest time, black holes were like ghosts in the universe. We knew they were there, although we knew this mathematically, observationally, and theoretically, but we couldn't actually see one. It was like an emotion. You could feel their effects but not see them. The very idea of seeing them seemed impossible. After all, a black hole doesn't let light escape. And if something can't emit or reflect light, how do you take its picture? It felt like trying to photograph the wind. But in April 2019, something extraordinary happened. Humanity saw its first image of a black hole, and it was nothing short of a scientific miracle. This wasn't just any black hole. The target was a supermassive one lurking at the center of a galaxy called Messier 87, about 55 million light-years away. That's a distance so vast it's hard to even comprehend. And it wasn't small by any stretch of the imagination. It's about 6.5 billion times bigger than the Sun, so it is befitting to say that it was a cosmic heavyweight, pulling stars and gas into its gravitational grip like a celestial whirlpool. But the question remained, How could anyone capture an image of something that defies visibility? The answer came in the form of the Event Horizon Telescope, or EHT, a global network of radio telescopes working together like a single Earth-sized camera. It wasn't just one telescope snapping a picture. It was a coordinated effort involving observatories scattered across the planet, from Hawaii to Chile, from Spain to Antarctica. They synchronized their observations to such a degree of precision that it felt like orchestrating a symphony where each instrument was thousands of miles apart. It was an incredible achievement of engineering and teamwork. What the EHT captured wasn't the black hole itself. Remember, it's pitch black and absorbs all light. What the EHT captured was the glowing gas and light swirling around its edge, just outside the event horizon. This is the point of no return, where gravity is so strong that nothing, not even light, can escape. The image showed a ring of light, almost like a fiery halo, with a dark shadow in the center. That shadow wasn't the black hole directly, but its silhouette, cast by the bending of light as it tried and failed to escape the gravitational pull. When the image was unveiled to the world, it was a moment of collective wonder. Scientists, journalists, and the general public stared at this glowing, donut-shaped marvel, realizing they were looking at something that had existed in theory for over a century but had never been seen before. It wasn't just a simple, meaningless picture. It was proof, a glimpse into one of the universe's most mysterious and powerful phenomena. The image itself wasn't high definition, and some people joked that it looked like a blurry bagel, but the significance was monumental. The project didn't happen overnight. It was the result of years of painstaking work by an international team of over 200 scientists. They had to gather and process an enormous amount of data, so much that it couldn't even be sent digitally. Instead, hard drives had to be physically transported between observatories for analysis. The computing power needed to stitch all this data together was staggering, and the final image was the result of algorithms so sophisticated they seemed like magic. At the center of this groundbreaking achievement was Dr. Katie Booman, who became one of the faces of the project. She developed an algorithm that helped turn the raw data into the iconic image we now know. Booman and her team's work showed how collaboration and innovation could push the boundaries of what humanity can achieve. It wasn't just about science. It was about people coming together to do something no one had ever done before. This first picture of a black hole was more than just a scientific milestone. It was a humbling reminder of how small we are in the grand scheme of things and how much there is left to learn. It showed that even the most daunting mysteries of the universe could be brought into the light, one discovery at a time. And while it answered some questions, it also raised new ones. What's happening in that shadowy core? How does the gas move and swirl at such immense speeds? What secrets does M87 star still hold? The image of M87 star wasn't the end of the story. It marked a new era of black hole science, where we could not only theorize about these enigmatic objects, but also observe them in ways that we never could. And in that glowing ring of light, the universe seemed to whisper, there's so much more to see. But while the future of black holes in space is still unknown, an uncommon source accurately predicted what a black hole would look like, and you could never guess where the unintended prediction came from. Most accurate prediction of black holes, Interstellar. The source is none other than Interstellar, the epic sci-fi movie which was released in 2014 that takes you on a mind-bending journey through space and time, didn't just aim to tell a story, it wanted to get the science right. That's rare in Hollywood, where explosions and drama are often more important than facts. But Christopher Nolan, the director, had something different in mind. He wanted the black hole in his movie Gargantua to look and behave as realistically as possible. To make that happen, he didn't just rely on special effects wizards. He brought in a real-life physicist, Kip Thorne, whose work on general relativity and astrophysics helped shape how the movie portrayed black holes. Kip Thorne wasn't just an advisor who occasionally popped in with notes. He was deeply involved, making sure that every detail of Gargantua was grounded in actual science. Thorne and the visual effects team used real equations to create the stunning image of the black hole. They didn't just guess what it might look like. They crunched numbers and ran simulations based on Einstein's theories of relativity. These calculations showed how light would bend and twist around a black hole due to its immense gravitational pull. What they came up with wasn't just pretty, it was groundbreaking. When you see Gargantua on screen, with its glowing, swirling halo of light surrounding a pitch-black center, You're looking at something that's as close to reality as human imagination and technology could get at the time. The light bending around the black hole isn't just a cool visual trick. It's what would actually happen if you could observe a real black hole up close. The light from stars behind the black hole is dragged around by its gravity, creating that bright, warped ring. This effect, called gravitational lensing, had been theorized for decades, but Interstellar brought it to life in a way no one had seen before. In fact, the visualizations were so accurate that they ended up contributing to science itself. While working on the movie, Thorne and the effects team discovered details about how gravitational lensing works that hadn't been fully explored before. Their work was later published in a scientific paper, making Interstellar not just a film, but also a contributor to astrophysics research. It's almost as if Hollywood and science joined forces to pull back the curtain on one of the universe's greatest mysteries. But Interstellar didn't just predict what a black hole might look like. It also delved into what it might mean to interact with one. The movie plays with the idea of time dilation, which is a real effect predicted by Einstein's theory of relativity. Near a black hole, time moves slower for someone close to it than for someone farther away. In the film, the characters visit a planet orbiting Gargantua, where an hour on the surface equals 7 years for people back on their ship. While the extreme nature of this time dilation was exaggerated for dramatic effect, the concept itself is rooted in solid science. The movie also explores the idea of what might happen inside a black hole. When the protagonist, Cooper, crosses Gargantua's event horizon, he ends up in a surreal, multi-dimensional space called the Tesseract. This part of the film is more speculative, as no one really knows what happens beyond the event horizon. Physics as we understand it breaks down, and we're left with theories and imagination. Kip Thorne ensured that the portrayal didn't outright contradict known science, but he allowed for creative liberties to fill in the gaps where our understanding ends. The point is that Interstellar didn't only entertain its audience, it also educated and inspired. For many viewers, it was the first time they truly understood the mind-bending nature of black holes and relativity. The movie sparked curiosity, leading people to learn more about the real science behind what they'd seen on screen. Even scientists have praised the film for its effort to balance storytelling with accuracy. Gargantua became a cultural touchstone, a visual representation of black holes that resonated with both experts and the general public. What's remarkable is how Interstellar bridged the gap between science and art. It showed that you don't have to sacrifice one for the other. By staying true to the physics while embracing creative storytelling, it gave us a glimpse of the universe's most mysterious phenomena in a way that felt both awe-inspiring and believable. But we can't talk about predictions of black holes and black holes as a whole without talking about these next two juggernauts. So stay tuned. Albert Einstein and Michio Kaku's take on black holes. The first is none other than Albert Einstein. Now, although he is one of the greatest minds in human history, he didn't exactly warm up to the idea of black holes at first. With all his equations that describe the fabric of the universe, some of those equations suggested something so bizarre, it felt almost unreal. Black holes weren't called that in his time. They were theoretical oddities hinted at by his own theory of general relativity. The math suggested that if an object became dense enough, its gravity would create a point of no return, a singularity where all the normal rules of physics would break down. Einstein found this idea unsettling. Even though the math was solid, he famously thought nature wouldn't allow such a strange thing to exist in reality. Einstein's skepticism didn't come from a lack of imagination, but rather from his deep respect for how beautifully predictable the universe seemed to be. Black holes, with their infinite density and the possibility of tearing space-time apart, felt too chaotic for his taste. He acknowledged they were theoretically possible, but doubted they'd ever form naturally. Yet, as much as Einstein might have resisted the idea, his own equations laid the foundation for everything we know about black holes today. It's a bit like building a door you don't expect anyone to walk through, only to find that not only is the door real, but people are already stepping inside. Now let's leap forward to Michio Kaku, a theoretical physicist who embraces black holes with a kind of childlike wonder and enthusiasm. Kaku has a knack for explaining complex ideas in a way that feels like storytelling, and when he talks about black holes, it's as if he's describing an adventure into the unknown. Unlike Einstein, who seemed hesitant about the concept, Kaku dives right into the possibility of exploring black holes and even seeing inside them. Kaku's fascination lies in what might be hidden beyond the event horizon, the boundary where everything, including light, gets swallowed up. While conventional physics tells us that crossing this boundary leads to inevitable destruction, Kaku speculates about more extraordinary possibilities. He often brings up the idea that black holes might not just be dead ends, but could also serve as cosmic portals. In his vision, the singularity at the center might connect to another part of the universe, or even a different universe altogether. This concept isn't just wild imagination, it's based on theoretical ideas like wormholes, which are solutions to Einstein's equations that describe shortcuts through spacetime. Kaku's view of black holes is filled with questions that make your mind spin. Could advanced civilizations one day harness black holes as gateways for interstellar travel? Could information somehow survive the journey past the event horizon? These ideas are speculative, of course, but they show how far we've come from Einstein's cautious approach. Instead of seeing black holes as terrifying voids, Kaku sees them as puzzles waiting to be solved, and maybe even opportunities for exploration. When it comes to the idea of actually seeing inside a black hole, both Einstein and Kaku bring different perspectives to the table. Einstein's work suggests that time and space would stretch infinitely as you approach the singularity, making it impossible to observe what's inside in any traditional sense. To him, the singularity was a place where the laws of physics as we know them completely break down, meaning there's no clear way to predict or understand what's happening beyond that point. It's like trying to read the last page of a book that's been torn out. Kaku, on the other hand, plays with the idea that future breakthroughs in technology or understanding might let us peer into this mysterious realm. He speculates about hypothetical scenarios where we could bypass the destructive forces of the event horizon or even decode the information that black holes supposedly trap. One of his more intriguing ideas involves the concept of holographic principles, which suggests that the information inside a black hole might not be lost but could instead be encoded on its surface. Like a cosmic library we just haven't figured out how to read yet. Do you think we will eventually be able to see inside a black hole? Share your thoughts with us in the comments section. Remember to like, share, and subscribe for more. Also, click the next video showing on your screen. You will enjoy it.